Welcome you all. Today we are going to discuss one more problem in the alternative fuels. The question is, a four-stroke diesel engine is running on diesel pungania methyl ester blend 40% with an equal ratio of 0.8. The air and fuel enter an engine 25 degrees centigrade. The exhaust is at 527 degrees centigrade. And the heat rejected to the coolant is 3000 megajoule per kilomole of fuel. And the heat rejected through the coolant is 3000 megajoule per kilomole of fuel. 1. Write the equations for stoichiometric combustion and the actual combustion. Second, by calculating the enthalpy of the exhaust flow, deduce the specific work output of the engine. Deduce the specific work output of the engine and thus the overall efficiency. If the engine has a swept volume of 6 liters and a volumetric efficiency of 72% based on the airflow, calculate the power output at a speed of 1500 rpm. The ambient pressure is 1 bar. State clearly any assumption that you make. The given that a 4-stroke diesel engine, the blends diesel, pungania methyl ester, that is biodiesel, equivalent ratio 5 is equal to 0.8. Air and the fuel enter the engine at 25 degrees centigrade, that is equal to 298 Kelvin. The exhaust gas temperature 527 degrees centigrade, that is equal to 800 Kelvin. Heat rejected to the coolant is 3000 megajoule per kilomole of fuel. Ambient pressure is 1 bar. State clearly any assumption that you made. Now, write the equation for stoichiometric combustion and the actual combustion. Second, by calculating the enthalpy of exhaust flow, deduce the specific work output of the engine and thus overall efficiency. Third, if the engine has a swept volume of 6 liter and the volumetric efficiency of 72% based upon the airflow, calculate the power output at a speed of 1500 rpm. Solution. First assumption is there is no dissociation occurs. The second one is the fuel molecular formula diesel is C14.4 H24.9, then biodiesel C18 H35O2. The calorific value of the diesel fuel is 42.5 megajoule per kg, whereas in the case of biodiesel is 37.425 megajoule per kg. Now, the first one is the stoichiometric combustion equation is 0.6 kilomole of diesel plus 0.4 kilomole of biodiesel reacted with Y amount of O2 plus 3.76 N2 produces A amount of CO2, B amount of H2O, C amount of N2. Now, the stoichiometric air required for combustion of the fuel, we know that the combustion equation, that is Y is equal to A plus B by 4 minus B by 2. Now, for our case, Y is equal to 0.6 multiplied by 14.4 plus 0.4 multiplied by 18 plus 0.6 multiplied by 24.9 plus 0.4 multiplied by 35 over 4 minus 0.6 multiplied by 0 plus 0.4 multiplied by 2 over 2. We get 15.84 plus 28.94 by 4 minus 0.8 by 2. So Y is equal to 22.675 kilomole of air per kilomole of fuel. Therefore, the stoichiometric combustion equation becomes 0.6 diesel plus 0.4 biodiesel reacted with 22.675 O2 plus 3.76 N2 produces 15.84 CO2, 14.47 H2O, 83.603 N2. Answer 1A. Now, the equivalent ratio phi is given as 0.8, that is equal to stoichiometric air-fuel ratio over actual air-fuel ratio. So, actual air-fuel ratio is equal to stoichiometric air-fuel ratio 22.625 over 0.8. We get 28.344 kilomole of air per kilomole of. Therefore, the actual combustion equation becomes 0.6 diesel plus 0.4 biodiesel, then 28.344 O2 plus 3.76 N2, 15.84 CO2, 14.47 H2O, 106.57 N2, and this 28.344 minus 22.625, that is equal to 5.699 O2. This is answer 1B. Now second question is specific work output. The fuel at 27 degrees centigrade, that is 0.6 diesel plus 0.4 biodiesel plus air, that is 28.344 O2 plus 3.76 N2. This all together, that is enthalpy of reactant, then enthalpy of the product, that is exhaust given as enthalpy of the gas at 800 Kelvin, then the heat rejected to the coolant, that is equal to 3000 megajoule per kilomole of fuel. Then specific work output. When you are making a steady flow energy equation, heat enthalpy of the reactant is equal to enthalpy of the product plus heat rejected plus specific work output. Then work output is equal to enthalpy of the reactant minus enthalpy of the product minus work output, that is in 4. Now for enthalpy of the reactant is equal to enthalpy of the diesel plus enthalpy of the biodiesel, that is 0.6 into enthalpy of diesel, 0.4 enthalpy of biodiesel plus 28.344 enthalpy of air. So for finding out the enthalpy of combustion of diesel and biodiesel, so we need to find out this enthalpy of the reaction for any fuel which contains CaHbNCOD plus Y of O2 plus 3.76 N2 produces ACO2 plus B by 2 H2O plus CN2. Now this enthalpy of combustion, that is lower heating value, that is equal to enthalpy of reactant minus enthalpy of the product. Here the enthalpy of the reactant is air plus fuel. In this case the enthalpy of the product is CO2 H2O N2. So we can find out this enthalpy of the reactant is equal to lower heating value plus enthalpy of the product. This is equation 5. So we can get this enthalpy of the product, so that at 298 air is equal to 0, N2 is equal to 0, O2 is equal to 0, CO2 393.512, H2O 241.824, H of CO2, H of H2O, H of N2 at 298 Kelvin, that is equal to minus 393.512 megajoule per kilomole. Here minus 241.824. This one is equal to 0, and the enthalpy of air is equal to 0, so that they given the lower heating value of diesel is equal to 42.5 megajoule per kg. So we have to convert this into kilomole. C 14.4 H 24.9 molecular weight is equal to 14.4 multiplied by 12 plus 24.9 multiplied by 1. We get 197.7. So 197.7 kg per kilomole. Kilomole per kg we can get 8402.25 megajoule per kilomole of fuel. Then for H of diesel is equal to 0.6 multiplied by 8402.25 plus 14.4 mole of minus 393.512 plus 24.9 by 2 minus 241.823. We get minus 275.0176 megajoule per kilomole of fuel. Then for the case of biodiesel, C18 H35 O2, so we get 18 CO2, 17.75 H2O. Lower heating value they given as 37.425 megajoule per kg on kilomole basis, that is 37.425 multiplied by molecular weight 18 into 12 plus 35 into 1 plus 2 into 16, we get 283 lower heating value of this biodiesel is equal to 10591.275 megajoule per kilomole of fuel. Therefore, this enthalpy of biodiesel is equal to 10591.275 plus 18 into minus 393.512 plus 17.75 multiplied with minus 241.823. We get enthalpy of biodiesel is equal to minus 723.861 megajoule per kilomole of fuel. Then enthalpy of air is equal to 0, that already we know. Then enthalpy of the product, that is equal to N of CO2 multiplied by H of CO2 plus N of H2O multiplied by H of H2O plus N of N2 multiplied by H of N2 plus N of O2 multiplied by H of O2 at 800 Kelvin. So N of CO2 is equal to 15.84, H2O 14.47, N2 106.57, then 5.699 at 800 Kelvin. CO2 minus 370.699, H2O minus 223.831, then N2 15.042, O2 15.837, minus 370.699, for 2O minus 223.831, for N2 15.042, then for O2 15.837, we get minus 5871.872, for H2O minus 3238.834, for N2 1603.025, for O2 90.255. So this summation enthalpy of product at 800 Kelvin is equal to minus 7417.425 megajoule per kilomole of fuel. Apply enthalpy of the reactant, enthalpy of the product and the heat rejected to the equation 4. We get specific work output is equal to 0.6 multiplied by minus 275.0316 for diesel, 0.4 multiplied by minus 723.861 for biodiesel, minus of minus 7417.425 minus 3000. We get specific work is equal to 3962.911 megajoule per kilomole of fuel. This is answer 2A. Now the second part of the question number 2 is overall efficiency. So that is equal to work output divided by lower heating value of the fuel. That is equal to 3962.911. Already we derived for diesel. It is 8402.25 multiplied by 60% plus 10591.275 multiplied by 0.4%. We get efficiency 42.71. Answer second B. Now the third question is power output of the engine. So this power output of the engine is equal to moles of fuel multiplied by specific work output of the engine. Specific output we already get from the question number 2B. Now this mole of fuel we have to get from the given data. The given volumetric efficiency is equal to 72%. We know that the definition of volumetric is equal to actual volume over volume equivalent to the set volume. So here this efficiency is equal to actual volume over set volume multiplied by N over 2 into 60. So we get actual volume is equal to volumetric efficiency into set volume multiplied by N divided by 2 into 60. The volumetric efficiency they are given 0.72. Set volume they are given 6 liters. 6 into 10 to the power minus 3 meter cube. This N is 1500 rpm over 2 into 60. We get volume of air is equal to 0.054 meter cube per second. and then volume of the fuel is equal to volume of air over air fuel ratio, that is equal to 0.054 over 28.344, then 1 mole of air plus 3.76 mole of N2, we get 4.0024 into 10 to the power minus 4 meter cube per second. Then we know that ideal gas relations PV is equal to N R naught in T. So here N is equal to PV divided by R naught into T. So P pressure is given 1 bar into volume is equal to 4.0024 into 10 to the power minus 4. R naught we know 8314 and temperature 298 Kelvin. We get N is equal to 1.6154 into 10 to the power minus 5 kilomoles N of fuel. So the power output is equal to 1.6154 into 10 to the power minus 5 multiplied by 3962.911. That is equal to 0.06554 megajoule per second. That is equal to 65.55 kilojoule per second. That is 65.55 kilowatt. This is answer 3. If any doubt, you can place in the comment section. Thank you.
Subscribe to our channel. Like if you're satisfied, and share because it may useful to someone.